Hello and welcome. My name is Yohannes Abate. I'm a professor of physics at the University of Georgia. My guest today is Professor Michael Kosterlitz. He is the winner of the 2016 Nobel Prize in Physics. And Professor Kosterlitz, thank you for accepting this invitation and welcome.
Oh, I'm glad to be here.
So I would like to start our conversation with an important topic, very dear to your heart, rock climbing. So I know that you are a passionate climber, and in fact there is, if I get it right, there is a route, a hiking route or so, named after you in the 60s in Italy.
Right. There was, well, at that time I was a very enthusiastic rock climber, and I was on in Torino on a Royal Society fellowship. The skiing season was over, and so I was going crazy because I was a very enthusiastic rock climber, so I needed to get out into and do some rock climbing. And I happened to get to know some of the younger climbers in Torino in Italy, and one day we're driving up in one of the passes on the way to the Alps, it's called the Val d'Orco. Going up this narrow little road up this valley, I saw this boulder, big stone, about, I don't know, 6-7 meters high, high enough that if you fell off it, it might hurt. And there was this gently overhanging face with this thin crack running up it. And I thought, wow, that looks like a nice problem. So I yelled in my pidgin Italian, stop the car, I want to try this climb. So I put my climbing shoes on, and to my surprise, I managed to get up this crack. And I thought, oh, that's nice, that was fun. Then we went further up and did some more, one or two other climbs. But this boulder problem started taking on a life of its own, because it turned out that nobody could repeat it for a number of years, although a lot of people tried it and fell off and so on. So it became quite well known, and eventually it got its name, Fissura Kosterlitz. In other words, the Kosterlitz crack, which you can interpret as you like. Not so long ago, I happened to be in Italy and visit the little village slightly higher up the valley called village of Cerasoli, and was taken out to dinner by the mayor of the little village, who informed me that this little boulder with the crack running up it was actually an important made an important contribution to the economy of the village, because a lot of people came to try the boulder problem and spent money in the village. So I therefore became an honorary citizen of this little village of Cerasoli.
Very interesting. So what is it about climbing? Is there any relation with physics? Like, it's fun, of course, but it is super risky, and
in a very it's related in a very sort of distant fashion, in the sense that physics and climbing, there's a lot of uncertainty uncertainty. Of course, in physics, the only penalty for failure is possible embarrassment. In climbing, the penalty for a mistake and failure is up to and including death. So the penalties are a little bit more serious.
Right, absolutely.
Right.
Absolutely. maybe before I ask you about the discovery and the work you did that led to the Nobel Prize, it'd be good to talk a little bit about topology. So topology was an important, you and David Thales came up with this terminology, topological long-range order. And what is topology? I actually brought a couple of interesting geometrical entities that you probably have never seen before. I don't know. This one is a coffee pot, an Ethiopian coffee pot, and has a seat, and you can open it and close. So this has a different topology. I mean, it has one hole here. If you open it, we'll have two. Right. And then I have also a Klein bottle. This is the famous Klein bottle. So how do we classify these kinds of stuff in terms of topology, with their topological,
Well, of course, when I started, I had no idea about, I knew that topology was a branch of mathematics, but that was all I knew. And so, I was viewed things from the statistical mechanical point of view. And so I was interested in superfluidity in a thin film. And so the only excitation that can destroy superfluid flow are vortices. There's nothing, these things that go round like water running out of through the plug hole when you empty a bath. Those are the only excitations that can destroy the superfluid flow. It's rather surprising, but quantum mechanics says that those are the only excitations that can destroy the superfluid flow. And therefore, the problem reduces to the statistical mechanics of a bunch of vortices. And vortices are high energy configurations, but statistical mechanics says that anything that can happen will happen, but with some probability. And of course, vortices have high energy and therefore occur with very low probability, but they must be important because they're the only excitations that can destroy superfluid flow. And therefore, these are the entities that must be responsible for any transition that might occur in such a film. Yeah. Now, of course, at the time I didn't know, I knew this language, but I had no idea that there were topological excitations. So I didn't know. Wouldn't know a piece of topology that sat up and barked. But then, of course, David Thales, who I was working with, and David Thales was a genius who knew everything about everything. And he was the guy who coined the phrase topological excitations. After all, the superfluid velocity is defined basically by its gradient of the phase of the wave function. And that's the only piece of quantum mechanics we need to think about. The rest of it is purely classical. Now, the point is that the circulation of the phase as you walk around the center of a vortex must, as you walk around, the system is described by an order parameter, which is a complex field, which has to be single valued. Mm-hmm. Therefore, the phase can change by a multiple of 2 pi, but changing as you walk around the some singularity or vortex core, the phase can change by some multiple of 2 pi. And that defines the topology. Okay. So Thales pointed out these vortices, which are responsible for what happens in these films, he coined the phrase topological transition, because the topology of the vortices is very simple, but fortunately for me, I didn't have to understand that this was topological.
It's very interesting that the power of mathematical description, right? Like for a topologist, these two are similar, right? They're very different for us, but as a topologist, they're very similar in that they have one whole, and that kind of thinking allows one to do, to describe very complicated things such as these phase transitions and that sort of thing. And the what I want to follow up with this question is that the this power of mathematics in general, right? You think, do we discover mathematics, or do we invent it?
I think we invent it, because to my way of looking at it, the job of a physicist, whether experimental physicist or theoretical physicist, is to describe the real world. And in order to describe it, we need some tools. And the best tool we have is mathematics. And of course, the only difficulty is that a piece of mathematics is a self-contained, internally consistent theory, if you wish. And when you hope that the physical situation one is trying to describe fits into this piece of mathematics. May or may not, because after all, the real world does what it does. It doesn't care about your mathematics, it doesn't care about my mathematics. But mathematics is the best tool at our disposal to describe the real world, and with a bit of luck, the real world obeys the mathematical laws. So it's up to us to construct or dig out the piece of mathematics that works.
Okay, I see. So in going back to the original work which you did in 72, the short paper, and then in 73, the paper was multiplied by 10 times in terms of page number, because you worked out the mathematics in detail. Right. So, I guess when I first looked at the first 2 pages, it contained most of the main results, right? So what was the transition? So you wanted to elaborate that more? Is that what happened?
These papers described, the physical mechanism of the transition. Yeah. And of course, once we'd found out what the physical mechanism was, the next step was to try to, to understand the theory of it, and try to work out the theory behind it. And this turned out to be fairly complicated, because basically what happened was one can transform it into the problem of a plasma of an overall neutral set of charges interacting, the Coulomb interaction, and in 2 dimensions, the Coulomb interaction Coulomb energy is proportional to the logarithm of the separation. And this was an unsolved problem, because this 2-dimensional Coulomb gas had never been solved. So that was the mathematical problem we reduced our physics to. And so, that was really what the problem which we sort of solved.
So I want to ask you the implementation of your work. Now, the field has grown quite a bit since you and David Thales begun this topological thinking, and it has even trickled down into photonics and phononics in my field, in optics. And do you follow these advancements? And it's quite powerful that those ideas have gone into different fields in physics.
Well, of course, I mean, needless to say, I'm very pleased to see that the ideas have taken off, but a lot of them I don't really follow because I'm getting too old to keep up with all the modern developments. But it's fascinating to realize that what started off as a intellectual exercise to try to sort out some contradiction between theory and experiment has evolved into something much more than what we started out to do. Yeah. It's very gratifying. Right. But of course, we had no idea when we started that this was going to happen.
Yeah, that's the most interesting part. You have this fascinating story that, that was your first postdoctoral work, right? Yes. That ended up, I mean, there's no better word than luck. Is that the word that we should use for this? Or, it's amazing that you run into this amazing problem when you start a postdoc. I mean,
well, right. I mean, it's like what I keep on saying that, if you're going to win some major prize, it's sort of 95% dumb luck, and the rest is, you need some smarts to be able to do the necessary arithmetic. But it's the dumb luck that's the most important. You got to find the right problem at the right time, the right people in the right place, and there's no way of arranging all that stuff without. That's a dumb luck part. Right.
But you have to realize it when you see an interesting problem. So that's not luck.
Right. Oh, of course, one's got to basically one's got to get turned on by it.
Yeah.
And when Thouless sort of started, the thing that turned me on was Thouless pointing out you got this conflict between present theory and experiment. It's clear that something was wrong with the theory, and so that was just something to me that needed resolving this problem. And I thought, okay, surely it's possible, because the theory is sitting there, and these ideas of David's about just knowing that these vortex excitations were the only thing that can be responsible for the transition in a superfluid film. Right. And then you can shout the words topology, because the quantum mechanical phase when you went round the center of a vortex, had to change by a multiple of 2 pi to keep the wave function single valued, as it had to be. From that point on, it was just a matter of putting things together. Well, it was more than just a matter. Right.
But absolutely. It's but the original, I think, finding the right problem and working with the right person.
Yeah, that was the right problem, and the sense. And I always felt, even when I couldn't do anything, I couldn't solve it, I always felt that we had the right ingredients. Mm-hmm. And all it needed was a little bit of intelligence to be able to put it together into some sort of coherent theory to be able to say something significant.
Okay.
And so I thought, okay, this is what physics should be. Here we got all this, we got this observation, they got a contradiction that needed fixing, and we have the mechanism. So it's like putting together the pieces of a puzzle. And I had a lot of fun doing it. So, of course, it wasn't just fun, it was also obsession. Certainly, I can't say that I got completely obsessed by this problem. I would spent basically, even when I thought I was doing something else, I was, my brain was always working on it, trying to figure it out. Even with my rock climbing, when I was sitting on a ledge, holding the rope somewhere way up in the cliff, my attention would wander, and I would see the image of these vortices moving around and doing the thing, and I would, basically lose all sense of where I was. So this problem took on a life of its own.
Wonderful. So in the original paper in the 73, 72, this experimental disagreement with, the line versus the, that was an important, observation that, needed a solution, like you said. So I want to ask you this crosstalk. I'm an experimentalist between, theory. You've also done a lot of simulation with David Landau and others, and experiments. I mean, looking at all of this as the synergy, the crosstalk between these. Has that, in your career, new research, this crosstalk, was that important? How did you, take advantage of this, or what is your view on all of this, the three things together?
Okay, well, for me personally, I never did experimental physics because I didn't enjoy doing experiment. And actually, I got the impression that experiment and me were definitely like oil and water, in the sense that if I were to walk into an experimental lab, things would promptly stop working properly. And so I decided that if I'm going to do physics, I'm going to have to do theory, because I got bored with doing experimental physics. I just wasn't good at it. And for some reason, experiments went wrong for me.
So you realized that early on as an undergraduate, or?
I was an undergraduate when I realized that experimental science wasn't for me. For example, in Cambridge, I did a course on biochemistry. And one of the practical experiments, I had ended up with this test tube full of basically a colorless liquid. And I was standing there staring at it when suddenly it started changing color. And I thought to myself, this doesn't look good. So I held it as far away from me as I could, and then it exploded. So from that point on, I decided that any experimental work for me is a bad idea. And theory was the only thing that in physics also, I decided physics was a safer subject.
In what way did you think it was safe?
Well, physics couldn't hurt me.
Oh, yeah.
In the sense that, because, when this damn test tube blew up.
You mean theoretical physics?
Yeah, theoretical physics couldn't hurt me like that, because I got shards of glass on my cheek, and it was a bit annoying. Right. And also, I had no idea that a test tube full of colorless liquid could suddenly change color and blow up in my face. It's dangerous.
But on the other hand, your mathematics was very strong. Do you think that contributed for you being a theoretical physicist, or you liked mathematics as well, or what is the relationship between?
I can't say that I liked mathematics, but I could do it. Mm-hmm. And so theoretical physics was something that I could cope with, if you like.
I see. Yeah. So, you talk a lot about David Thales. You had a huge regard You
Yeah,
know,
well,
you
I mean,
compared him with even, like
yeah, Feynman, Schwinger,
Feynman or so.
you know, the giants in the field. I mean,
Right,
I view
right.
David Kosterlitz on the same, you know, as one of the giants.
So what was your interaction with him? Unfortunately, he passed away a few years ago. But what was it like being his postdoc, and later on, afterwards, you know, your interaction with him? And
But, though actually it wasn't his postdoc. The thing was that in Birmingham, I had this. It was a departmental postdoc,
I see.
and so I was, you know, able to work with whoever would work with me.
I see.
I when I went to Birmingham, I was a high energy physicist, but there was so much competition in the field that I just couldn't, you know, being completely isolated, I just couldn't compete. So I was looking around for something to do, and so eventually I talked to Thouless, and he basically suggested I look at this problem.
So that was an important encounter to meet.
Right, that's part of the 95% done
Right,
work.
exactly. But looking back, in addition to you know, meeting David Thouless at the right time, what other things, you know, the main things that contributed to your success from childhood, adolescence to adulthood? What do you say, like the main things are that?
Of course, one very important thing was the influence of my father, who was claimed to fame as the discoverer of some of these neuroreceptors, you know, enkephalins, which are basically a small version, a smaller molecule, but with the same sort of properties, similar properties to the endorphins. And he was also in the so-called opioid field, and you know, if he knew what his work had turned into, the opioid crisis, he would be turning in his grave. He had a very strong influence on me because he said, look, I wanted to do theoretical physics, but his father would not pay for his education unless it meant something medicine related. And so he became, he actually became a doctor. But then he wasn't interested in patients. He turned to research. You know, several people have said that, you know, he should have won a Nobel Prize, but he didn't. But certainly his influence was very, very, very important. He basically said, I should study what turned me on. And it didn't matter what the field was. And of course, I can remember a maximum of 10 facts, but I'm not too sure of the last 4. So what I can't deduce from 6 facts, forget it. And the only field that allows you to work with only 6 facts is physics or mathematics. So that's basically why I'm in that field.
So your father was a big influence.
Oh, huge influence. I mean, he said, you know, I should do what I want, what turns me on. Mm-hmm. No, that's my advice to young students, is that, you know, do what you're good at and what turns you on, and have fun with it, because if you don't have fun, life is not worth living.
Right. Right. If you aim for a prize, you might not get it, and you're miserable, so you lose both.
Right. I mean, I was very lucky,
right.
But I would have a pretty satisfying career if I hadn't got a prize. Because I enjoyed what I was, you know, I had fun with what I was doing.
Yeah. So, you know, just wanted to ask you about, you know, you have family of children, right? And how was that, during those days with physics and climbing and then family? How are those, mixed together or, balance them and be successful?
Right. I had a very understanding girlfriend/wife because I made it fairly clear that I had, that I had my order of priorities at the time was the first top was in the list was climbing, second was physics, and the third was family. And
you got away with that?
I got away with it. As I said, I got a very understanding wife who, supported me all the time. Eternally grateful to her, because but.
So an understanding wife is
right.
Very
at the time, I decided that I had to put my cards on the table so there'd be no misunderstanding later on what my priorities were. So I just laid it out, and if she had decided that that was not satisfactory.
This was before marriage?
Oh, yeah.
Oh, wow. That is very interesting.
Yeah, because I decided that I don't want to be in a relationship where my twisted priorities were discovered, and that might be a disaster. I thought I'd put my cards on the table, be completely open about it, and if my wife was still prepared to put up with me, that would be wonderful. And if she wasn't prepared to put up with it, it's better to break up now rather than later. So I was very lucky that she accepted my priorities, and
so that's let's say behind a great man is a great woman.
A great woman, yes.
Right, and she's been you've been married how many years now? That's
a long time. We got married.
That's a challenging question.
We started a relationship in 1963, 62 or 63. And we got married in 1970. Yeah, we got married and got a postdoc in Italy in 1970. And we got married in Italy. That was fun because a man from Britain marrying a Swedish girl in Italy at the time was pretty unusual. And we decided that we'd had so much help from my Italian colleagues that we'd do this, we'd get married on our own. We'd arrange it on our own. And that was an interesting experience because we started off at the town hall where we announced that we wanted to get married. And so we filled out some document, and then we got it signed, and then we got shuffled off to next office. And gradually we signed more papers, and this pile of papers grew and grew and grew. And after about a couple of days of this, we started getting a bit suspicious that maybe we were just getting the runaround, which was when we found ourselves back in the office we'd started, we realized, yes, we were getting the runaround. And so we went back to the physics department where we conferred with the director of the institute, who I think he misunderstood things. Because remember, our Italian wasn't brilliant. And he said, okay, look, we'll all go back tomorrow and sort things out. At least that's what we thought he said. Remember, our Italian wasn't brilliant. And so got a bit nervous when he and the secretary turned up dressed to the nines. We thought, oh dear, do they think we're going to get married or something? Because, all it was trying to sort out this paperwork. However, we walked to the town hall and went into the room, this big room we had this runaround. Entered the room, and then the director said, just wait. And then he saw a flunky in the distance. And the flunky came scuttling over, and there was this whispered conversation. And the flunky lost a bit of colour, went a bit pale and so on, and then scuttled off. And about 2 minutes, and the director said, just wait. It's all right. Everything's going to sort itself out. This column of bureaucrats who we all recognise as having been giving us the runaround for the past 2 weeks lined up in front of us and apologised. I've never seen anything like it. He was standing there apologising to us for his screwing us around. And then within the next 15 minutes or so, all the discrepancies in the paperwork that had grown up due to our misunderstanding, not understanding Italian too well, were sorted out, straightened out. All the documentation was completed, and we're all set to, all the formalities were then completed, and we're all set to get married. Then, we got married in this, civil ceremony, and had a little reception in our little apartment which we'd rented. That was the end of
the ceremony.
Yeah, the ceremony. It was fun.
But, what about later when children came and, balancing? Did you keep your words, climbing first, physics second, or
yes.
did it change?
Yeah,
somehow?
Well, the point was that we had come to this, we'd made this contract that this was the way we do things.
So kids did not change the order?
Well, eventually, of course, the order of priorities did change, but to start with...
that's a good...
we got on okay.
I see. Yeah, so I want to ask you about what you think about the current status of condensed matter physics compared to what it was 50 years ago. What do you think is the current developments in your view?
When you figure out something, some part of physics, there's always something new.
Right.
No matter how far you think physics has developed, it'll never be finished. There's always be something new. I mean, okay, for example, today there's the problem of out of equilibrium systems.
Yeah. I was going to ask you about that.
Not much is understood about these.
Yeah.
It's a whole gigantic field. I mean, especially if you think about the fact that almost everything you look at in the world is a driven out of equilibrium system.
Absolutely.
Whether it's a living person, or it's some inanimate object. There's nothing that's truly in equilibrium. And so the days of equilibrium physics are pretty much over, and that much of it's on the slopes. After all, equilibrium is the boring state that everything eventually evolves to. But there are other states that systems will evolve to, but they're equally important. And these are out of equilibrium driven systems. And particularly one could regard an adult animal like you and me as a driven out of equilibrium system. After all, we're certainly driven, but we'll die without taking food, consuming food and stuff. And the equilibrium state for us is a state of death. But once we reach the adult state, basically we're all roughly the same. We're all evolved to roughly the same driven out of equilibrium state. We're tubes about 2 meters tall with 4, 2 arms, 2 legs, etc., etc. Question I wanted to, started asking myself was, why the hell does that happen? Why does the system reach a well-defined stationary state, time-independent state? What happens?
Right.
Now,
and why that specific type of state? Very defined.
Well, I can understand that because, there will be some, if you like, deterministic, defined mechanism, but surely we have evolved from, there are probably many paths humans could take.
Right, exactly. That's my point. Why a particular kind?
Right. Yeah. And so I asked myself that question, and one of the things that I found missing from all the treatments was, what about the stochastic noise, the random noise we're all in contact with? For example, we live in a bath of viruses and bacteria, which from our lack of knowledge, we could regard as random noise.
Yeah.
And so I thought maybe one should take this random noise seriously and see what effect that has. And so one can model this in a fairly simple way, and there's one simple model which does display most of the observed phenomena in not in biology but in physics. Things like periodic systems, spatially periodic systems, et cetera, et cetera, et cetera. And then I thought, okay, this is a simple model we can study, but I'd like to know what the effects of this random noise is, which nobody had really thought much about before. And then, I looked at it numerically and found, wow, it does seem to lead to we used a model where you had infinity of possible patterns, and discovered to our amazement that it was actually the stochastic noise that picked out a unique pattern. We were,
Interesting.
I had this idea.
Did you do anything to the noise, or it's
No.
just freely?
It's completely
noisy.
random.
I see.
Gaussian distributed noise with zero mean, et cetera, simplest possible thing. The only variable about the noise was strength.
It's extremely interesting that, it works in spite of, maybe because of the noise.
I think it's because of the noise. I don't think people have thought about this deeply enough, because normally one thinks of this random noise as just something that screws things up.
Yeah. In physics, you want to, in experiments, as much as possible, suppress noise. That's your goal.
But you mustn't suppress it too much, because without noise, if you assume that your system is described by some differential equation, no matter how nonlinear, if you don't have any randomness on it, it'll never lead you to some unique final state, because the state
could be deterministic.
If it's deterministic, the state you end up will depend on the initial conditions.
Right. Nothing interesting. You know already before.
Right.
Yeah.
But then if you add some stochastic noise on, then what happens is that you end up with in a unique state that's independent of how you started off, and then the next step in the argument is, okay, maybe this is how we would describe this evolving biological system, and that's what the only people I know of who are interested thinking along these same lines are particular people in China who I'm working with, and we hope
there is a big community of stochastic thermodynamics now.
Right.
People are thinking about these non-equilibrium systems, and very, very exciting problem.
Yes.
But let me ask you on this. Okay, the noise could do something,
Right.
but how can the noise continue to do things that would end up, with some sort of thing that we, from anthropomorphic point of view, we consider functional, like the heart or, things like that. You see what I mean? It can create some kind of, pattern, that's fine, but it would have to continue to do that.
I mean, I'm thinking in terms of an evolving system.
Yeah.
Now, and I want to think about a system that evolves into a stationary state, a time-independent state.
Okay, I see.
But once you're in the time-independent state, it's going to stay there forever.
Yes. Okay, so you're just going to like a pattern or some sort.
Right.
Okay.
I mean, that's the first step.
Yes.
If one can understand this problem,
Right.
then somebody else can go further.
Absolutely, I see.
But this problem is difficult enough.
Right.
And it's actually
so.
also,
What is
it's also heretical enough that it's fun.
I see.
I love doing things that people find heretic.
It's very,
think
very
of as
general.
heresy.
Very, very exciting. What is the current status of this work then? We have a solution yet, or
it's
coming, or
we got somewhere with it, but all we managed to do is understand a very simple model. Mm-hmm. But it's nothing.
Well, let me stop you right there about these simple models, because even your original work was simplifying sort of what was observed and be able to mathematize that and get something out of it. So, is that sort of an important, way of thinking, right? To try to simplify things, but not too far simple that it's out of reality. I mean, is there a balance, sort of?
Well, at the moment,
yeah,
the model we're looking at was designed to be computationally as simple as possible. Of course it's non-linear and insoluble, but the non-linearity is the simplest one we can think of. And then we just add some noise to it and see what happens. So that's where the field sits right now. But if we let our minds wander and so on, it's possible that this style of thinking may be relevant to more relevant problems. And we really believe that, for example, it might be relevant to, evolution problems in evolution.
In what sense?
Well,
try to explain emergence, or
yeah.
Okay, I see.
We can regard the deterministic part as
a start.
As a start. The mechanism that leads to some sort of adult form, and then the stochastic noise as refining down the possible adult, the permissible adult forms, if you like. I mean, that's the dream. We're certainly not there.
Yeah, I see. What about in physics? Do you see application of this? Well, simple experiments, or some experiments could be done to.
Okay, we haven't thought that far. I mean, at the moment, we're just working on very simple models.
Okay. I see.
If you like, a couple of toy models. Yeah. But we do think that the results are relevant. And it would be great if somebody would be able to apply this to something a bit more realistic.
Yeah, I see. From the beginning, that was sort of an important way of thinking about problems for you, right?
Yeah.
So, can you say something about, trying to model things in such a way that are simple, but still captures, the essence of reality?
Well, the model we're talking about in physics does display a lot of the properties one can observe in various out of equilibrium systems. For instance, like in directional solidification, processes of that nature. Mm-hmm. But the model is also designed to be as simple as possible from a computational point of view. Because after all, if you're trying to simulate something for very long times, you need something simple and computationally as friendly as possible.
Okay, wonderful. So fortunately, we're running out of time, but I wanted to ask you this question on, for young, enthusiastic, high school students, undergraduate students, graduate students, and researchers in general. Mm-hmm. What's the advice you have, like from looking back and sort of some things you could say?
Find something you're good at and something that turns you on. Because in physics, for example, any phenomenon that's not understood is going to be difficult. And so you've got to be, in order to do anything about it, you're going to have to be turned on by the problem, in other words, excited by it. Otherwise, you probably won't get anywhere because, these problems which nobody understands are not easy. You've got to be really turned on in order to work hard at it. Basically, the best advice I've got is find something that turns you on and gives you fun trying to do it, because having fun is very important. Life is not worth living without having fun. So really, that's the best advice I can give.
Thank you very much, Professor Kosterlitz, for your time. It was wonderful talking to you.
Very welcome.